Good morning, Pre-Calculus Honors students, for your penultimate lesson of the semester, Modeling Periodic Behavior in 8.4. So we're going to use trig functions to model periodic behavior, and that is we're going to graph more complicated sine curves. So we already looked at the effects of A and B on A sine bx and A cosine bx, but you can translate them horizontally h and vertically k. Remember, the x minus h is a horizontal shift of h to the right. Y minus k is a vertical shift of k up. So give the equation of the sine wave shown below. Well, let's get some of the key information off of this and see what we can come up with. Okay, a lot of kids like focusing on the cosine because it's easy to find the peaks. And sure, if we got a peak here at 3,5, and then we have another peak here at 11.5. So that from peak to peak is the period. So we get the period is equal to 8. And if you remember from our form, 2 pi over b is equal to the period. So you get 2 pi over b equals 8. So 2 pi equals 8b. So b equals 2 pi divided by 8. Or b equals pi over 4. So that's the coefficient. That's actually a capital B they keep using. Now what about the amplitude? The amplitude is the max minus the min divided by 2. And so our maximum is 5. The minimum is down here at -1, and we divide that by 2 and we get an amplitude of 3. So that means our A coefficient is going to be 3. And now we have to figure out the h and k by thinking about how far is this shifted over. Well, it's important to look at the midline. Well, actually, in this case, we can just see that, right, if the amplitude equals 3, we want to go 3 down from 5 to get to 2. And so this midline is this line like this. Let me make a better line. Very key idea here. The midline of the graph is the horizontal line halfway between the max and the min. It can help you see that this is going to be our complete cycle for the sine here, for the cosine, like this. We're going to get this much of it. And it starts here, and it's been shifted over 3,5 from, but careful now, this cosine would normally start here and go mama and end up here at 8,3. So you see how it's been shifted over 3 and up 2. So our horizontal shift is h equals 3. The vertical shift is k equals just 2. Let's see how this all combines in our final equation then. So we've got the vertical shift here, the horizontal shift over here, our amplitude A, figured out up here, and notice how this B factor comes into play, right there. And we use the factored form that I mentioned in the standard form before. And that way we can make sure it does it in the right direction, as we discussed earlier in chapter 4. Now let's say you liked using sine instead, and you said, oh, I see the midline all right. Here's the midline, halfway between the max and the min. And I'm going to aim for sine this time instead. The sine going like this. Well, we're going to borrow the same amplitude and period again, and so they're going to have the same A and B. So A will still be 3, and B will still be pi over 4. It's just that the shifts change a little bit when we think of this as a sine. The sine is going to start at 0 normally, and with an amplitude of 3, it would go up to 3 here over a period of 8. So the sine would look something like this, and now it's been shifted. It's been shifted. Let's look at the shifts. We moved it up 2 and over 3. here's the starting point, I'm sorry. We're starting here at 1, 2, normally it'd be over here, so it's only up 2 and over 1. So, sure enough, there's our sine wave. And let's go over the different parts of this. There's the h, that's the horizontal shift of 1. Here's the vertical shift up of 2. And we have the amplitude, A. And here, we found this by using the period. Remember, the period is 2 pi divided by b, so b is 2 pi divided by the period. And the period was 8 in this case. Okay, now let's look at a word problem. The depth of water at the end of a pier varies with the tides throughout the day. Today, the high tide occurs at 4:15 a.m. with a depth of 5.2. The low tide occurs at 10:27 a.m. with a depth of 2. So let's incorporate these into a graph. Find the trig equation that models the depth of the water t hours after midnight. So we've got this peak here at 4.255.2 and a nadir down here at 10.45, 2. That's the low tide, high tide to low tide. Now you might wonder what happened to 4:15. Well, 4:15, I have to take 4:15, take those 15 minutes and multiply by 1 hour over 60 to get 0.25 hours. And that's the same thing I do with changing 10/27, 27 60ths, actually ends up being 0.45. Okay? So I want to change them into a decimal so we don't have to keep changing from hours and minutes. Now, what type of trig function we use? Well, let's go ahead and try the cosine. And with the cosine here, we have to figure out, first of all, where's this midline here? Let's get that drawn in. The midline should go halfway between these two, roughly in here somewhere. And so for the midline, I'm going to go halfway between the peak, which is at 5.2, and 2. Divide that by 2. 7.2 over 2 equals 3.6. So that means I've been raised up 3.6 from the normal midline here. So that means our K is going to be 3.6. We're shifting everything up that much. Now, the amplitude then, we can do max minus min divided by 2. We can also see how this is above the midline. 5.2 minus 3.6 is 1.2. No. 1.6. 1.6 for the amplitude. So we've got our amplitude A of 1.6. We should also figure out the period. For the period is equal to 2 pi divided by b. So b equals 2 pi divided by the period. Well, what is one complete period here? Well, from 4.25 to 10.45, that is basically a half a cycle. So half the period equals 10.45 minus 4.25, and that's 6.2. So the period equals 12.4 hours for the period. So we divide that out, and you can come up with an exact B of pi over 6.2, or let's calculate that out to be 0.507 roughly. Now we still need the shift over, and we can get that from our first peak here. Normally the peak should be right here at the on the y-axis, so it's been shifted over 4.25. So our h shift, our shift to the right, is 4.25. So we can incorporate all these ideas then into our diagram. There's our shift, there's h, our shift to the right. There's k, the shift up. There's the amplitude A that we figured out, and there's that B that we figured out from the period. Now find the depth of the water at noon. Well, we just put timing 12 to our equation, sub it into the equation, so t equals 12, put it into the equation, and solve for the unknown depth. You get about 2.47 meters. Now, a large boat needs at least 3 meters of water to moor at the end of the pier. During what time period after noon can it safely moor? Well, similar to last time, now we're going to go in the other direction. We're going to take d equals 3, the depth equals 3, and put in for d, and start solving. So I put 3 in for d, subtract 3.6 from both sides, divide both sides by 1.6, take the inverse cosine, and we get 1.96 when you do the inverse cosine, negative 0.375. Notice the inverse cosine gives a second quadrant angle. But any angle coterminal to 1.96 would also work, like negative 1.96. So we get a lot of different possible answers for that. And you remember we can judge this from our circle. The calculator just gave this 1.96 answer out here. We said negative 1.96 could also work. But we could also go around the circle completely again. So I added 2 pi onto negative 1.96 to come up with another possible answer. So, and also you get another 2 pi onto 1.96 to come up with this answer. And when we solve those separately, we get times of 8:06 a.m., 12:48 p.m., and 8:30 p.m. We're interested in the time after noon that it can safely moor. So noon is right here. Here's noon. So we're looking at these two answers, D and E. So when can it safely moor? Between, you can see that's going to be above 3 in between these values, between 12:48 p.m. and 8:30 p.m. You have to subtract 12 from that to get from military time to normal time. Okay, now 8.4, relationships among the functions. We're going to simplify trig expressions, improve trig identities. And you've seen all these relationships before in Algebra 2 Honors, but I want to help you memorize all these because that's what you got to do. There is no formula sheet on this. You got to know all your Pythagorean relationships and reciprocal relationships and so forth. These are the reciprocals. Remember, we start out with the basic ones in the calculator, sine, cosine, tangent. When you take the reciprocal of those, you get cosecant, secant, and cotangent. Relationships with negatives. Sine of negative theta equals negative sine theta, and so forth. Notice the pattern of these. The negative seems to come outside, but here the negative is ignored. That's because sine, cosecant, and tangent are all odd functions. Cosine, secant, and cotangent are all even functions. There's the Pythagorean relationships. Sine squared plus cosine squared equals 1. 1 plus tangent squared theta equals secant squared theta. 1 plus cotangent squared theta equals cosecant squared theta. And the cofunction relationships. That's where the co comes from in half the trig functions. Sine and cosine, tangent and cotangent, secant and cosecant. Now, let me help you see where these come from a little thing I did on GeoGebra. And here's the trig relationships. And you'd see them all in this diagram. Remember how we said sine and cosine were the x and y coordinates on a unit circle. So you see that right here, sine and cosine. And the first Pythagorean relationship comes from this triangle that we set up. This distance cosine, this horizontal distance, is also down here. So we have sine squared theta plus cosine squared theta equals 1 squared. Or sine squared theta plus cosine squared theta equals 1. There's your most fundamental Pythagorean relationship based on that right triangle. Now, remember how we defined the tangent as this segment on the tangent line. Here's this tangent line that's forming a right angle up here. And the tangent goes from this point of tangency out to the intersection of the tangent line with the x-axis. The secant crosses the circle in 2 spots, here and way back here. But the secant, the length of the secant is from the center of the unit circle out to this crossing point out here. And that's where we get another Pythagorean relationship. If you focus on this triangle, you've got 1 plus tangent squared equals secant squared, like this. So there's another key triangle. And here's your other Pythagorean relationship, 1 plus cotangent squared equals cosecant squared. Purple there. Now, you can also see in this diagram the reciprocal relationships. That is, as sine is getting smaller, see how cosecant in purple there is getting bigger. And they come together and both equal 1 at 90 degrees. Similarly, cosine, as it gets bigger, secant gets smaller, and they come together at 0. In fact, notice what happens here. We've got a bunch of functions that act together here in terms of their undefinedness. Tangent and secant. At 0, they go to 0. But at 90, notice how the tangent and secant spread out more and more and more, and eventually they don't touch, so they become undefined. So tangent and secant are undefined up here at 90 degrees. Whereas, in retrospect, at 90, cotangent and cosecant go to 0, whereas, or cosecant's at 1, cotangent's this little length, and here that goes to 0. But then as we come down this way, notice at 0 degrees, the purple and blue lines become parallel and they become undefined. Okay, and there's lots of other relationships inside here too. And we'll explore those a little later in the section. So, from this, you should be able to write all your Pythagorean relationships and reciprocal relationships on this, what I call this benzene ring of the trig functions. So sine and cosine are related with sine squared plus cosine squared theta equals 1. You should print this up and jot them down. Cosine and secant are in a reciprocal relationship. That's why I put a single bar in between here. So cosine theta equals 1 over secant theta. Secant and tangent, we talked about this big triangle. 1 plus tangent squared theta equals secant squared theta. Cotangent and tangent are in a reciprocal relationship. They equal each other at 45 degrees. But then as the tangent gets smaller, the cotangent gets bigger. So tangent theta equals 1 over cotangent theta. Cotangent and cosecant are in a Pythagorean relationship. You can see it in this triangle right here. 1 plus cotangent squared theta equals cosecant squared theta. And finally, cosecant and sine. They're in a reciprocal relationship. As sine gets bigger, cosecant gets smaller. So sine theta equals 1 over cosecant theta. There's also ways to cross across the middle and see if you can figure out these. That is, sine and cosine can be connected to relate to tangent and also to cotangent. That is, sine is to cosine, big leg is to short leg, as, now look at the big triangle here, big leg tangent is to short leg. So the tangent theta equals sine theta over cosine theta. These relationships were basically mentioned on page 282. If you want to look them up in your book. But they're called the quotient identities. And basically they say tangent of theta is sine of theta over cosine of theta. And cotangent of theta is cosine of theta over sine of theta. And you can see that with this triangle here. If we look at the one here, because this is sine, this is cosine. And you can say short leg is to long leg, cosine theta is to sine theta. As, now look at this right triangle, cotangent theta is to 1. Okay, let's try some proofs. Here we go. Simplify secant x minus sine x tan x. Well, the secant is 1 over cosine. The sine, we're going to leave that as normal, and the tangent is sine x over cosine x. So we get 1 minus sine squared x over cosine x. Notice we conveniently sort of had our own LCD ready to go here, cosine x. 1 minus sine squared x is cosine squared x. So we get cosine squared x over cosine x. So you just get cosine x for your answer. Cosine x. Now let's do this proof. And I'm going to start with something called the brute force method. Get everything in terms of sine and cosine. This is sort of the form of last resort, because we might see that there might be an easier way to deal with things. Cotangent of A is cosine A over sine A times 1 plus tangent squared A is going to be sine squared A over cosine squared A all over tangent A, which is sine of A over cosine of A, equals cosecant squared, which is 1 over sine squared of A. And if we get both sides to be the same thing, we should be okay. And this denominator kind of helps me out here because I can see if I multiply through first, and maybe we can understand what we can use for an overall LCD, cosine A over sine A plus, now when I multiply through here, one of the cosines cancels, one of the sines cancels, so I just get sine A over cosine A all over sine A all over cosine A. Notice I'm focusing on the more complicated side. Not much more we can do with this side. So now I'm going to multiply both sides by my LCD. The LCD in the format cosine A sine A, and the use of the LCD in this case is going to be to get rid of secondary fractions. So I'm going to multiply both the numerator and the denominator by cosine A sine A. And what does that create? Well, when I distribute this into both terms here, the sine a's cancel here, so I get cosine squared A, plus here the cosine a's cancel, so I get sine squared A, all over here just the cosine equals, so I get sine squared of A. And sure enough, that's our Pythagorean relationship. Cosine squared plus sine squared equals 1. So 1 over sine squared A equals 1 over sine squared A. And you're done. QED. That's the brute force method. The finesse method is to actually use your Pythagorean relationships. Okay, using the Pythagorean relationships on this one. First, you can see you only have one term over here, so anything you do to compact two terms like this would help. And 1 plus tangent squared is secant squared. All over tangent A equals cosecant squared, which is like that. Now, we can go a couple routes on this, but let's consider tan A and cotan A and come up with cotangent squared A times secant squared A equals cosecant squared A. Because tangent of A is 1 over cotangent. And so if I have cotangent all over 1 over cotangent, that's cotangent squared A times secant squared A. Now at this point, I would go to the trig functions cosine squared A over sine squared A. And secant is 1 over cosine squared A, just to quickly see how these two multiply out to be cosecant. That's not a real common one. Cotangent times secant equals cosecant. But I can show you that in the diagram, how that works out. And so then these cancel. And we're left with 1 over sine squared A equals 1 over sine squared A. You don't have to get both sides totally simplified. You just have to get both sides to exactly agree with each other. Now notice what I didn't do here. I didn't multiply both sides by tan A. That is considered illegal in a proof. In a proof, you don't know if this is equal yet. So you can't multiply both sides of the equation by anything or add anything to both sides of the equation. Now I put a bunch of these unit circle diagrams with all the trig functions on so you can see that there's so many different formulas you can come out from here. Just by looking at different Pythagorean, different right triangles. Let's try finding some of those. Like this one right here. that right triangle would say tan squared theta equals sine squared theta plus, and this length here isn't secant, this is going to be secant minus cosine. Secant theta minus cosine theta, all that quantity squared. And you can do a similar one with one over here to get cotangent squared theta equals cosine squared theta plus cosecant of theta minus the sine of theta, quantity squared. You can also come up with some by just doing some area ideas. Look at the area of this big triangle like this. Well, we can add that to our list of, also we can do a Pythagorean theorem on that too. We can say cosecant squared theta plus secant squared theta equals cotangent theta plus tangent theta, quantity squared. But we can also look at the area of the big triangle. This big black triangle has an area equal to 1/2 cosecant times secant. But it's also equal to 1/2 the base, and I can look at this hypotenuse as the base, cotangent theta plus tangent theta times the height, which is 1. So multiply through by 2, and you get cosecant theta secant theta equals cotangent theta plus tangent theta. Okay, and there's a lot more triangles that you can explore in this, but that's one way you can usually generate stuff that you can practice proving. Okay, flange out.